Lesson number 28, daily summary. In this lesson, we continue our work with algebraic fractions to include adding them and subtracting them. Number one, let's take a moment to recall how we add and subtract fractions with like denominators. For example, 2/3 plus 5/3. Well, clearly the answer is 7/3, but really what we're doing is combining those two fractions into one, taking advantage of the fact that they have the same denominator. So when we combine into a single fraction, we keep that same denominator. Notice that the 3's don't become a 6 down here or a 9 or anything like that, but the 2 and the 5's get copied just as they are, and then we add them together on the top, copy the 3 on the bottom, 7/3. Adding and subtracting fractions with like denominators works the same way for algebraic fractions. Let's try this one. So 9x squared plus 17x over 3x plus 4 minus 3x squared plus 9x over 3x plus 4. Hey, that's fantastic because the denominator is just 3x plus 4. So I will copy that denominator of 3x plus 4. I'll copy the 9x squared plus 17x. I'll copy the 3x squared plus 9x. Copy the subtraction sign right there. And now I have taken my two separate fractions and combined them into one. Now, I have made a very common mistake here, and I'm going to finish this and get the wrong answer, so don't copy this next part. But if we combine like terms here, 9x squared minus 3x squared, that's 6x squared. 17x plus 9x is 26x. So there's our answer. 6x squared plus 26x divided by 3x plus 4. And that is no good, because this subtraction right here was saying subtract this entire fraction from the first one, which really means subtracting this entire numerator from this numerator. And we accurately subtracted the 3x squared. There it is. But we didn't subtract the 9x. We added the 9x, and that's not what we were supposed to do. So to avoid this mistake, here's my strong recommendation. When you go from two fractions added or subtracted into a single fraction, put those numerators into their own bags, parentheses. But each of those numerators is a bag of stuff, and we were supposed to subtract the second bag from the first bag, parentheses, make it clear where the bags are. So let's get rid of those bags. So the first bag was not necessary, 9x squared plus 17x, but then the second bag was, because that minus sign comes in and changes all the signs in the second bag. So minus 3x squared we had, but then minus 9x, that's where we had a mistake, divided by the 3x plus 4. And then we combine our like terms. So 9x squared minus 3x squared is 6x squared. 17x minus 9x, that's 8x. So that's how we get to the correct answer right down here. Technically, we always need to simplify our fractions or check to see if we can simplify our fractions. So let's try it on this one. We're not allowed to cancel anything yet. Don't be tempted to cancel, for example, 6 and 3, or x with x, or 8 with 4, because there's additions and subtractions floating around. So last lesson we saw we're supposed to first factor top and bottom completely, and then look for common factors. So upstairs, the greatest common factor, it's, let's see, 2 and also x with a single set of parentheses. So what's left? 3x plus 4, great. The bottom, greatest common factor is 1. Is it a difference of two squares? No. Is it 2 by 2 boxable? No, it doesn't have an x squared, so there's nothing to do on the bottom. But I will point out there's a 3x plus 4 on the top and a 3x plus 4 on the bottom, and we get to cancel them. If you're not sure about that, because the bottom is addition, and I said you can't cancel when there's addition and subtraction, then throw it in parentheses, bring in the invisible 1, and then recognize that the top and the bottom are both multiplication, and they have a common factor. 3x plus 4 is a carbon copy on the top and the bottom. And so our final answer is just 2x over 1, or simply 2x. Okay, so adding and subtracting fractions, algebraic fractions with the same denominator is a piece of cake. But things get much trickier when the denominators are different. So let's first remind ourselves of what to do when the denominators are different. So let's take a look at this problem right here. 9 over 28 minus 3 over 40 minus 1 over 42. So these are not algebraic fractions, they're just ordinary numerical fractions. And we need to build a common denominator, hopefully the lowest common denominator or least common denominator, or LCD. Now, sometimes those denominators have numbers that are friendly enough, small enough, that I can just look at them and know what the greatest common denominator, the least common denominator is. But 28 and 40 and 42, I have no earthly idea what the smallest number is that all three of those go into. And so I'm going to show you a technique. It's going to be pretty involved, but it is a foolproof way of finding the lowest common denominator for numeric fractions, and the technique is going to extend to the algebraic fractions, which are the ones that we need to learn how to deal with. So bear with me as we go through this example. First step is to factor each of these denominators completely. And when I say factor, I mean go all the way down to prime numbers. So for example, 28 is really 4 times 7. 7 is prime, but 4 is not. 4 is really 2 times 2, right? And so 28 is really 2 times 2 times 7. It's right there. And you'll see that the 9 has been copied up on top. And then we do the same thing with 40. You might have seen this called a factor tree in some previous math class. Lots of ways to factor 40, for example, 10 times 4. 10 is really 5 times 2. And 4 is really 2 times 2. So there are our factors, 5 times 2 times 2 times 2. 40 is the same as 5 times 2 times 2 times 2. I like putting those factors in increasing order. And then the same thing with 42. Why don't you pause the video here, see if you can do the factor tree for 42, get all the way to primes, and then come back. Okay, so different ways to do it, but hopefully we end up getting 42 being 2 times 3 times 7. Okay, now that these denominators are factored completely, we're going to make all three denominators the same. We are going to make our common denominator, and we're going to do that by filling in what's missing. So for example, let's look at just the first two denominators, yellow and green. I'm going to look at yellow and ask myself, what is yellow missing that green has? Well, green has a 2 and a 2 and a 2 and a 5. And yellow has a 2 and a 2, great, so we got those two. But yellow does not have another 2, and yellow has no 5s at all. So yellow needs another 2 and a 5. So let's put in another 2 and a 5. But you can't go around willy-nilly multiplying denominators of fractions by 2 and 5 without, I mean, you'll have changed the fraction. But the way you pay for it, balance the scales, is to multiply the top by the same 2 and 5. And so this fraction is equivalent to what it was before. You can check, because like the 2 and the 5, I could cancel right away, couldn't I? It would be silly because I'd be going backwards. But I have just a foo-foo here. The 2 and the 5, top and bottom, they cancel. But putting them in there is something that's going to be beneficial to us. So the first denominator now has everything it needs from the second denominator. So let's look at the other direction. What is this guy missing that this one over here has? Well, let's see. This has a 2, and a 7. 2 and a 2 and a no 7. Let's give the second denominator a 7. And therefore, at the same moment, give the numerator a 7. And now if you look closely at the first two denominators, hopefully you see they are the same. I'm going to say these 5 numbers, but in increasing order. 2, 2, 2, 5, 7. And now these 5 numbers. 2, 2, 2, 5, 7. Great. So by filling in what's missing, we have made these two denominators exactly the same as each other. And now it's time to bring the third denominator into the mix. So let's look at that blue denominator and ask what it is missing. What is this one missing that this one has? All right, this one's got a 2, a 2, a 2, a 5, and a 7. There's a 2, but I don't see any other 2s. So it needs 2 more 2s, and it needs a 5 and a 7. Okay, it doesn't have a 5, so it needs a 5 as well, but it does have a 7, so we don't need one of those. So I think what we said is 2 more 2s and a 5. 2, 2, 5, and therefore on the top, the same 2, 2, and 5. So this denominator has everything this one has now. Why did I pick the middle one and not the first one? Well, it didn't matter. The middle one and the first one are the same, right? So like this guy also has everything that the first one has. So all we need to do now is check to see that the first two have everything that the third one has. Okay, so the third one has a 2, a 3, a 7, 2, 2, and 5. 2, 3, 7, 2, 2, 5. Well, this is almost all of those numbers. It's all of them except for the 3. So just look carefully, compare the two of them, right? 2, 2, 2, there they are. 5 and 7, 5 and 7. It's just the 3 that's missing. So let's go back after the fact now and give this one a 3, top and bottom, and give this one a 3, top and bottom. And so after all of that careful work, these denominators are identical. I will say these 6 numbers in increasing order: 2, 2, 2, 3, 5, 7. In increasing order, these 6, 2, 2, 2, 3, 5, 7. d6, 2, 2, 2, 3, 5, 7. So we have made all of the denominators the same, and in fact, we have built the lowest common denominator. It is 2 times 2 times 2 times 3 times 5 times 7. Okay, let's start pushing these things together. I'm going to multiply, what am I going to do? I'm going to multiply out on the top. So the first numerator is what I'm looking at here. 9 times 2 times 5 times 3. I'm going to use a calculator to help me a little bit here. So 9 times 2 times 5 times 3. Okay, so that's 270. Let's do the middle denominator, sorry, the middle numerator next. 3 times 7 times 3, that's just 63. I don't think we need a calculator for the rest of those. So the first fraction became, what did we just say that was? 270. So first fraction is 270 divided by, and then I'm just gonna, what am I gonna do? I'm gonna write this thing, but in increasing order. 222,357 minus the middle denominator, middle numerator, sorry, 3 times 7 is 21, times 3 is 63, over the same 2, 2, 2, 3, 5, and 7. And then the last one was a minus. Last numerator, 2 times 2 is 4, times 5 is 20, divided by the same 2, 2, 2, 3, 5, 7. All right, so let's squeezed in there. All right, good enough. Okay, and then let's smush together and get a single fraction with a single denominator of 2, 2, 2, 3, 5, and 7. There's a reason I'm not multiplying those through just yet. I will as my last step. So single fraction means single denominator. So we go 270 minus 63 minus 20. I'm going to try to follow my own advice before, and that's to put each of these numerators in their own bags. When you go from different fractions to a single fraction, give everybody a bag. In this case, it doesn't matter, but in some cases with x's floating around, it might. Okay, so now we're doing the arithmetic here. 270 minus 63, that's 207, and then we subtract 20, that's 187, divided by 222, 3, 5, and 7. And so the reason that I liked leaving that denominator in factored form is that it makes it easier to see if it reduces with anything in the numerator. So 187, if I could write that in factored form, then it would be easy to tell. So I will write it in factored form. I'll tell you, it's 11 times 17. You can just do some trial and error to get the factors of 187. And so the question is, does it reduce with anything in the bottom? 11 and 17, no, there's no 11s or 17s on the bottom, and all of these numbers now in the top and bottom are primes, so there's no common factors to reduce. And it's really easy to see that nothing from 11 or 17 reduces with the bottom because we left the bottom in factored form. And so now it's fair to multiply through on the bottom. 2 times 2 times 2 times 3 times 5 times 7. Actually going to cheat. I think the answer is just on the next page. Right there, 840. But if we had written 840 from the beginning, it would have been more work to tell whether 11 or 17 factors with any part of 840. So that's why leaving the bottom in factored form is typically good practice. Only at the very end here is it worth writing 840. Okay, so that's the answer right there. 840 was the lowest common denominator. All right, so let's see what we can do with x's. B. 3y plus 2 over y minus 5 plus 4 over 3y plus 4 minus 7y squared plus 24y plus 28 over 3y squared minus 11y minus 20. My goodness. Okay, so all of that is copied here. I see additions and subtractions, so that means I need common denominators. And in order to find common denominators, we're going to factor. Now, y minus 5, there's nothing to do. Greatest common factor, difference of two squares, or 2 by 2 box. None of those is applicable. So that one got copied. 3y plus 2 is just copied. 3y plus 4, not factorable. It's copied. So is the 4 up here. But there is work to do with this 3y squared minus 11y minus 20. Pause the video here, see if you can do a 2 by 2 box on that one, and come back when you've got the factors. So hopefully you got 3y plus 4 over times y minus 5 when you did the 2 by 2 box. And now that one is factored completely, and the numerator, you could try doing a 2 by 2 box on it, but do not. The only things we're trying to factor right now are denominators, not numerators. Just factor denominators completely, and we have. Okay, so now we're going to think about filling in what's missing. We're completing these 3 denominators so that they are all eventually the same. So let's look at the first 2 denominators. Here's a y minus 5. Here's a 3y plus 4. What do they have? What does the first one need that the second one has? Well, the first one needs a 3y plus 4. It needs the entire thing. So 3y plus 4 goes right there, and therefore goes right there, the entire 3y plus 4, which means we actually need a bag around that numerator. Okay. And then the second denominator is 3y plus 4. What is it missing from the first denominator? Well, it's missing a y minus 5, so let's give it a y minus 5, and therefore give the top a y minus 5. The 4 doesn't need a bag, but it's safest just to give every numerator a bag. And then these first 2 denominators now are the same. They both have a y minus 5 and a 3y plus 4 in different orders, but that's okay. And now we bring the last denominator into our view. What is the last denominator missing from the second denominator, for example? Well, nothing. They're both the same. So that means we don't have to do anything else. We have our lowest common denominator. All 3 of these fractions have the same denominator now. So that means that we are ready to push them all together into a single fraction. And so we'll give a single copy of the 3y plus 4, y minus 5. And then upstairs, keep these bags around everything for now. 3y plus 2 times 3y plus 4 plus, that's in between the first 2 fractions, 4y minus 5 minus 7y squared plus 24y plus 28. And I will say if we do the problem from this point, we're not going to get the right answer because I've made a very simple mistake, very common mistake. And that's that I didn't give a bag around the last numerator. This 7y squared plus 24y plus 28 was supposed to be subtracted in its entirety. All of it subtracted. But at the moment, I'm only subtracting the 7y squared, and I'm adding the 24y, and I'm adding the 28. We need to subtract the bag, so we really needed to give it a bag. There it is. Okay, now we got to do some expanding, some distributing here. So in the first 2 parentheses, we're just multiplying these 2 things, either FOIL or lobster claw or distribute. Here we go. 9y squared plus 12y plus 6y plus 8. Plus, now we're distributing the 4y minus 20. Now we're distributing the minus sign. That changes all of the signs. Without the bag, we wouldn't have caught the minus on the 24 or the minus on the 28. Divided by a single copy of this denominator. As I said before, leave your denominators in factored form. Always, always, always. Don't multiply out down there. In the same way that in that big numerical example we just did, we didn't multiply out the 2 times 2 times 2 times 3 times 5 times 7 until the very end. Okay, now we're looking for like terms. 9y squared minus 7y squared, that's 2y squared. Plus 12y plus 6y, that's 18y. Plus another 4y is plus 22y. Minus 24y is minus 2y. Now the constant terms, plus 8, minus 20, that's a minus 12. Minus another 28, that's minus 40. Copy that denominator in factored form. Okay, this might be the final answer, but it's still our obligation to see if we can reduce this fraction, get anything simpler. And the way we reduce is to factor top and bottom completely. Well, the bottom is already factored. That's why we left it in factored form, but we do need to factor the top completely. Always look for the greatest common factor first. In this case, it's 2. That's good. We pull 2 outside and get this. copying the bottom. And then can we factor anything in the parentheses on top? Well, greatest common factor is already out. Is it a difference of 2 squares? No, it's 3 terms. 2 by 2 box is the only other option, and it is 2 by 2 boxable. So pause the video and factor the thing in the top parentheses with a 2 by 2 box, and then come back. Okay, so hopefully we got y minus 5, y plus 4 in either order. And then now that everything is factored and everything is multiplication, we can cancel foo-foos, fancy forms of 1. So what do you see on top and bottom that's carbon copy? Y minus 5. So they go away. And we're left with our final simplified answer, 2 parentheses y plus 4 over 3y plus 4. It could be tempting to maybe cancel the y's. It could be tempting maybe to cancel the 4's. Or tempting maybe to reduce this 2 with this 4. Avoid all of those temptations. We no longer have multiplication on the bottom, so we cannot cancel. Okay, one last example. This next one requires that we correctly handle repeated factors. Here's how we do it. Okay, so take a look at this. It is 2 fractions subtracted, so we need a common denominator. And that means first factoring denominators completely. So x squared minus x has a greatest common factor. It's x. And when you pull that x out, you're left with x minus 1. So this denominator is now represented in factored form there. And then this guy is 2 by 2 box factorable. So you can do the work later if you want to, but it is right there. And then I will just point out that this x minus 1 doesn't get left out of the party. It is right there. Okay. Let's take a look at these 2 denominators now. One right here and one right here. And we're trying to complete them to make them the same. So what is the second one missing that the first one has? Okay, the first one has an x and an x minus 1. The second one does not have a plain x, so it needs a plain x. So we give the second one a plain x, top and bottom, which means the top actually needed a bag. What else is the second one missing that the first one has? Well, again, the first one has an x and an x minus 1, and the second one now has an x and an x minus 1. So the second denominator isn't missing anything. But the first denominator is missing some things. So the second denominator has x minus 1x, that's here already, but it also has this, x minus 1x plus 5. And so we need to give this denominator x minus 1, x plus 5, top and bottom. Turns out the 4 didn't need a bag, but I just like putting every numerator in a bag. And the reason that I'm including this example here is really not that different from the example we just did, but to point out that even though this one had an x minus 1, it needed 2. The first x minus 1 is this one, but it needs another one. You can't get away with having just a single x minus 1 here when there's a repeated x minus 1 over here. So now if you look carefully at our 2 denominators, you'll see they're exactly the same. X minus 1, x minus 1, x plus 5. X minus 1, x minus 1, x plus 5. You can read the rest of this example. I'm not going to go through it in the video here. You can just read through. It's now a standard kind of thing. I just wanted to make sure we could handle the repeated factors.